Now we'll move to our last podium presentation for today. For this section, Jack.
So hello everyone, my name is Jake and I'm going into my second year of electrical engineering. In this presentation, I will be discussing my summer research, which I've conducted under the supervision of Gerard O'Leary and Professor Roman Genov. The broad overview of my project is shown on screen. I have developed a base station for bidirectional radio frequency communication and electromagnetic induction charging of a neural implant. First, I will give a brief background of the lab that I was part of. I worked in the Intelligent Sensory Microsystems Lab, which is run by Professor Genov and is a part of U of T's Department of Electrical and Computer Engineering. In this lab, composed of primarily ECE students and researchers, we are focusing on a not-so-ordinary computer system, the human brain. Epilepsy is a neurological disorder which affects around 50 million people worldwide. This disorder is characterized by irregular brain activity. In fact, if we look at an EEG diagram of brain activity, we can see spikes when the seizures occur. The brain signals are transmitted as electricity through neurons. These signals can be measured and intercepted, preventing seizures from occurring. As engineers who focus on electricity and its transmission, we realize that this is a fantastic challenge. At the Intelligent Sensory Microsystems Lab, we are at the forefront of interfacing the brain and computers. My lab's goal is to create a fully implanted chip known as a neuromodulator to prevent epileptic seizures. Chronically implanted devices present several unique engineering challenges. First, the collected data needs to be transferred to an external computer for analysis and to train machine learning models. Second, any battery-operated device will eventually run out of power, thus creating a need for a non-invasive battery charging method. This presentation will address the design of a base station, which is a fully wireless solution for powering and data transmission. The base station includes a printed circuit board, which combines a Bluetooth low-energy transceiver and a Wireless Power Consortium 1.2 standard compliant wireless power transmitter. This presentation will elaborate on the development and design of each of the three major components of the base station: the radio frequency communication, wireless charging, and graphical user interface. Current progress has led to PCBs being sent from manufacturing and a functioning prototype using a commercially available Bluetooth integrated circuit. The next step in the research project is to evaluate the performance of the PCB solution. Like I said, there are three main components. First, a wireless implant requires a power source to recharge its battery. To overcome this issue, a primary coil will charge an implanted secondary coil through electromagnetic induction. Second, the data collected by the implant needs to be transferred to an external computer for analysis and the training of machine learning models. Finally, since this device is intended to be an off-the-shelf product, there needs to be a simple user interface. First, I will elaborate on the design of the wireless charger. At the heart is an NXP chip which adheres to the WPC 1.2 standard. This allows for a standardized and safe transfer of power. The charger has the capacity to detect foreign objects which are interfering with the transfer, as well as dynamically adjust the output due to the receiver's power needs. The two coils communicate with each other through backscatter modulation. Additionally, fail-safes have been built in to ensure that the temperature rise of the brain tissue is not increasing during the transfer. Temperature sensors will pick up the external as well as internal temperature, and the charger will adjust the power to prevent a drastic rise. The Bluetooth pipeline is created between two Nordic semiconductor chips. We are using the NRF 52840, which is equipped with Bluetooth low-energy technology. Although BLE is typically used for small Internet of Things applications, we've managed to hit the theoretical maximum data rate of 1 megabit per second. The current implementation of the Bluetooth pipeline is as follows. The transmitter connects to the receiver and the two negotiate the connection parameters. This includes the data length, connection interval, and others. The configuration of these parameters drastically affects the data rate. For example, if the data rate is set to 27 bytes, the data rate is approximately 250 megabits per second. However, at the maximum value of 251 bytes, we can hit 1 megabit per second. The other parameters aren't as easily decided, however. The connection interval can't be too low. or else not enough data will be transferred per interval. If it's too high, there will be serious delays if a packet is dropped. So a good middle ground is needed. After the parameters are confirmed, the transmission begins. Initially, the system struggled and dropped many packets. However, since then, I implemented a retrieval algorithm which detects and retrieves lost packets. Additionally, I've optimized the parameter setup to minimize losses. With these changes, the system is consistently hitting data rates of over 1 megabit per second while maintaining zero loss of data. The figure on screen shows how varying the data length affects the data rate. As you can see, the best data rate is achieved with the longest data length of 251 bytes. It is also interesting to note that there were 0 dropped packets during each of the tests. So, since it performed reliably during testing, it can be concluded that the Bluetooth pipeline is rugged and fully capable of transmitting large amounts of data. The power transmitter and Bluetooth ICs are combined onto a single PCB. This PCB fits onto the header of a Raspberry Pi. Data can be sent to the Raspberry Pi from the Bluetooth receiver through numerous different communication protocols: SPI, I2C, UART, and USB. The Bluetooth pipeline can be configured on the fly by way of the serial wire debug interface. The small size of this PCB ensures that costs stay down without sacrificing the quality of the design. The two biggest challenges was integrating sensitive radio frequency components with the high current power transmitter. To mitigate the effect of the high currents, physical distance was established between the two systems. Additionally, there are two nearly perfect ground planes, which help to reduce ripples in the voltage and current. Lastly, the use of decoupling capacitors ensures for a constant and smooth power supply. In order to facilitate easy testing, there are numerous test points and LED indicators on the board. This carefully designed board is the product of several revisions and iterations upon the design process. Lastly, I have begun working on creating a CAD model of the base station using SOLIDWORKS. This will be useful as the housing can be 3D printed for rapid prototyping and testing. In the image on screen, I have so far modeled the Raspberry Pi, the custom PCB, and the USB connectors for power and data transfer. The next step is creating the housing for these components, as well as including a small OLED screen. The CAD model has been extremely useful already, as it has highlighted some small errors in the component alignment. Although the PCBs have not been manufactured yet, I've tested my wireless framework. Using two NRF52840 development boards, I have uploaded the code from my Bluetooth pipeline. The data is being streamed from one board to the other, and then the data is being fed over serial to the Python GUI and parser. The parser cleans and validates the data before passing it on to be displayed on screen. In this video, we can see that I'm plotting a simple sine wave. Furthermore, I'm in the process of developing an SPI link between the development board and an INTAN amplifier. This will simulate the actual implant, which will communicate with the Bluetooth model in the same way. Using an oscilloscope, I will send waveforms to the INTAN IC simulating brain activity. This will then be sent wirelessly and analyzed. In conclusion, my summer work has been focused on designing all the components of a fully functioning base station which supports the wireless implant. I've gained experience in embedded systems, hardware design, radio frequency design, and processing. That concludes my presentation. Thank you to all the listeners and judges.
Judges, if you have questions, please ask.
Okay, that was a nice presentation. Maybe can you tell me what was there any part of the process that you were going through here where you had, what were the biggest surprises or stumbling blocks? Let's say if you imagine where you were at the start of the summer to kind of where you are now once you've kind of worked all of this stuff out. Where were the places that you found yourself getting tripped up, or what were the biggest challenges that you had along the way?
I would say that the biggest challenges was in the software development. So I learned C as part of my first year curriculum. And I really enjoyed it. I did very well in that class, so I felt really confident coming into this. However, the software that I was developing was built upon a framework that has been professionally designed, so it was a big step up from what I was used to. However, I knew the fundamentals, so it took a little bit of time to get used to code being a lot more complicated and much better designed. So I learned a lot in terms of how to design my code and how to have it readable and to function at a very high level.
Okay, thank you.
Thank you, Jake, for your presentation. And thank you all for your time and the presenters for all of your awesome presentations. This now concludes our podium section. Judges, if you have filled out the rubric through the online judging form, our judging director will be compiling the marks for the presenters very soon.